So let's start. Hi, everybody. Welcome. Hope your day has been going well so far. I'm assuming this is the last seminar in the graduate series for this semester. So I'll try to keep it brief so we can all go, and have fun. My name is Vasilis Kouzamanis, and currently I'm in my first year pursuing my PhD degree under the supervision of Dr. Dimitrios Kalliotis. Currently, our research aims to develop a better understanding of the fluid structure interaction phenomena occurring in the coastal regions during hurricane events. First, to give some background to the topic, we have to discuss and mention what exactly is meant by fluid structure interaction in civil engineering. So fluid structure interaction exists in its various forms in both natural and man-made systems. For example, the interaction between a tree and a wind, the groundwater and the soil are typical examples of the fluid structure interaction that happen in nature. However, the nature of the interaction between the solid and the fluid in these problems are different, and they are really not the same. All these problems come under the vast category of fluid structure interaction, which abbreviating as FSI for the next slides. It is important to note that the degree of severity of interaction between the solid and the fluid varies between different problems. So, as you can see in the slide, how does the fluid flow interact with the solid structure? So basically, for those of you who may have a grasp of fluid mechanics, you could probably guess which terms of Navier-Stokes equations are transferred in the solid. But in a very simplified manner, there exists an interface surface. Let's say, for example, to give a realistic example, let's say the facade of a building, of a high-rise building, okay? So the wind, fluid, exerts pressures on the facade. The facade then transfers the pressures based on the characteristics of the fluid flow to the main loading bearing system of the building. So basically we have the fluid, gas or liquid, exerts pressures, and maybe, this pressure depends on the velocity and generally the characteristics of the fluid flow into the surface of the solid, which is traction, and then the solid deforms under those loads. So then what happens is that the solid deforms, right? So you can see, like in the graph, it's not in the original shape as it was. So that means that the fluid flow now changes. It governs around the deformed body. So the fluid interaction also takes the deformed solid structure, updates, let's say, the mesh of the domain, how you want to call it, and then the fluid flow must deform itself to capture the new shape. Now in typical civil engineering applications, the subject is usually classified based on the nature of the structure interacting with fluid. For example, the structure can be assumed to behave as a rigid body, no deformations under the fluid flow, or to deform the fluid flow in real time in each time step, so the fluid flow will update itself. Okay, so we said it can be also regarded as a rigid body or as a deformable body, but which one is the correct assumption? Well, there's no simple answer to this question, but as a rule of thumb, you would want to use the two-way FSI, which means deformed body, when you expect large deformations in flexible systems, which could in turn influence the fluid flow greatly. So to make this more clear, you can see the two movies in the slide. When you're solid, when you don't expect basically big deformations in the solid, there's no way to use two-way fluid structure interaction, because you're gonna be spending computational effort and modeling effort in something that will not influence the fluid flow greatly. However, when you expect large deformations, as the lower movie shows, you can see how basically the fluid flow changes dramatically based on the deformations that the flexible body has. Okay, so where does this leave us in terms of civil infrastructure? Well, those of you who are familiar with bridge engineering have already guessed that wind loads are basically the critical design of such cases. However, fluid structure interaction goes beyond that scope, goes beyond bridges. And we can actually attest to this, the case of coastal housing under hurricanes. Fluid flows can be important to the structures as well, since they experience both wave loading due to storm surging, I'm referring to coastal housing right now, and extreme wind loading during hurricanes, for example, in the roof. Of all recorded weather disasters in the US history, tropical cyclones have caused the most deaths and destruction. Expected annual economic losses from those types of damages caused by hurricane winds and storm-related flooding total around 54 billion to 34 billion in most cases as losses to households. Just, I think you remember Hurricane Ida. It was recorded as the 5th costliest tropic cyclone on record, and it threatened more than 8,100 homes with storm surges of over 10 feet, while the reconstruction cost value of those damaged homes was more than $120 billion. So if we take a summation, the total estimate of economic losses between 96 and 2012 amounts to $250 billion. Now, one would actually ask, so how would climate change, because it's like a hot topic and it's around everybody's lips these days, how would climate change affect hurricanes and the expected damages that will occur annually? So there hasn't been a consensus so far in the scientific community. However, many global climate models have estimated that with a warmer climate, the atmosphere is able to hold more water, which makes sense, right? And in turn will cause hurricanes to become quote unquote wetter, meaning amongst bearing other consequences that hurricanes such as Ida, in terms of rainfall and consequently storm surges, will become more common. So as the population density rises in coastal regions of the United States, there are some concerns about the associated increase in coastline construction of light frame timber houses and the vulnerability to wave and storm surge loads that can be generated from tropical storms. Currently, in order to escape those storm surges and water-induced damage, FEMA promotes guidelines for elevating houses above the base flood line. However, storm surging is not the only critical danger during a hurricane, since the most commonly damaged part of a home is the roof during a hurricane. For example, during Hurricane Ida, 25,000 properties were flooded by the storm. However, nearly 90,000 homes in the greater New Orleans area were left with poor housing conditions. Thus, it becomes quite clear that elevating coastal houses more and more is not a panacea. There is still a lack of knowledge on how light frame timber housing is going to perform in the next decades. So our research aims to better assess the wave surge interact with coastal houses on 2 standpoints. The first one is, so we want to study the effect of timber connections in light framed elevated coastal houses. How moment resisting timber connections versus conventional screw type connections may affect the response under wave loading. And then secondly, is we want to study how flexible timber pile foundations play into this role, how foundation flexibility and different soil properties might affect the response of the whole structure under hurricane loads. Okay, so let's start with modeling. For this study, we used an already existing coupled Eulerian Lagrangian fund element framework, and we used a commercial software called Abacus. Starting from this, let's say, bigger picture, to capture the fluid flow, we simulated the incompressible form of the Navier-Stokes equations, which you can see in the slide, for Newtonian fluids. So basically, the first equation is the conservation of momentum, and the second one is the conservation of mass. You can see the different terms that play into account in those equations, and basically, we're going to talk later about this, but the fluid structure interactions happens with this term here, like this basically the transfer of external loads and forces. This is how Navier-Stokes is updated. So in our simulations, both water and air were modeled by the use of Mie-Gruneisen equation of state. I really don't think I should go into much detail here because we could spend the next 30 minutes into this topic. But basically, this equation is kind of similar to the all known to us, the ideal gas flow equation, PV equals nRT, and it relates pressure and volume in a closed energy system. Moving forward. So the next step would be to actually capture the fluid structure interaction that happens here. So what would be the first step? The first step is for you to solve the fluid equations, right? So you can get the pressures and maybe the wall shear on your structure. So the coupled Eulerian Lagrangian framework uses this particular method. It's called immersed boundary method, which in simple words assumes a structure and its Lagrangian mesh submerged into the fluid domain, which is Eulerian. However, as one can imagine, in most cases, those two masses or those two geometries don't coincide. And that can be a problem as far as finite element method goes. It is necessary to implement a coupling mode, generally either ALE, arbitrary Lagrangian Eulerian, or IBM, used in this case, to transfer fluid information to the structure and back to the fluid itself. I want to spend some minutes more on this slide because I want to really kind of explain how this method works, because I think, at least I find it interesting. So you have to imagine you have two grids. The first grid is a Eulerian mesh. You can see in the slide is a black grid, basically. We should not imagine the points as water particles or fluid particles, rather than positions fixed in space where you install velocimeters and other data acquisition systems, just to capture the output variables of the fluid domain. Then you submerge your solid structure, let's say a ball, into the fluid. And of course, most of the times these 2 points don't coincide. So you have the solid boundary, which you should capture the interpolation between the fluid node and the solid node with the fluid structure interaction method. So to give a brief explanation about the methodology that this works, the first step would be to calculate the force densities of the elastic structure caused by the fluid on the boundary. The structure then will deform a finite amount and the boundary will follow its movement. So this is basically the FQT term here. Then what happens is at the second step, the transfer of the elastic deformation energy of the immersed structure in the nearby fluid nodes. For example, let's say that here you have the elastic force density. It must be transferred somehow to the nearby fluid nodes. So there are a lot of methods to do this, and basically, guess the extrapolation of how this can happen. Let's say, for example, ghost nodes, but it goes too far. But the main idea is that the Eulerian points that are nearby to the Lagrangian part will receive the biggest effect. Now, lastly, since the Lagrangian part has been formed, the Eulerian part is the same because it's Eulerian, but the fluid, the Navier-Stokes equations must be updated to account for the new velocities. Okay, so moving forward, how does the fluid interact with the surface apart from those integral equations that must be solved? We saw earlier. In most, I would say in most, that's a over-exaggeration, but in most fluid computational fluid dynamics, we have the so-called no-slip boundary effect. That means basically that the fluid velocities on the solid boundaries will equal to that of the solid boundary itself. So what this means, if the solid part, Lagrangian, doesn't move, then the velocity of the fluid on those nodes must be zero. There are two ways the no-slip condition is implemented typically. Either as a kinematic constraint, you can see that actually in the finite volume method a lot, or as an it's enforced by a penalty method, which means like friction. Which should we use? Which is better? Which gives better results? Which represents the natural world more realistically? I would argue that in a finite element method, because as we saw earlier, you have to solve for the velocities of the boundary. Implementing a boundary condition when you also have to solve for the displacement is not a good idea. It creates a lot of convergence problems and is not suggested. So what we've done actually in the study is we implement the no-slip boundary condition by assuming a near infinite, because it can't be infinite, a near infinite friction coefficient in the boundaries. That way we can ensure that the fluid basically has a zero velocity or the same velocity as the structure at that boundary, but also that it doesn't create problems in the convergence. Okay, so before diving into our main simulation, we had the validation. We had performed a validation study with the comparison of the test data. Let me actually move Zoom because I think it might hide anything. Okay, so this experiment was conducted as part of the NEAR facility at the Oregon State University. The experiment was basically a standard experiment of a wave maker pushing basically the water in a wave tank all across the beach slope when it encountered a rigid specimen. Then the pressures and the velocities were captured, velocities, of course, on the fluid part and pressures on the solid part. Okay, so what kind of waves do we produce to study this phenomenon? I mean, both the validation study and also in our study, we used solitary waves. The reasoning behind that is because solitary waves are a specific form of waves, which their nonlinearity basically counters the trout of the wave and just leaves a crest. This way, we feel it's much more easier and intuitive to relate and understand how the wave interacts with the structure, because you don't have another wave coming in. This is the equation. It's called Goring's normalized equation. I've explained and annotated the terms here. I don't think I need to go through them though. Okay. Moving forward. So to validate our way of thinking, our modeling, we compared the wave profile in the flume of the experimental data, and in our finite element modeling. Overall, I would say the comparison is fair. We had a problem of capturing the 10th wave gauge, which is actually after the slope nearby the solid specimen, where we estimate a bigger wave than what they had in their experiments. We're still trying to figure out why this happens. Again, we must realize that the Navier-Stokes equations are being solved for incompressible form, which is totally fine, but our mesh was kind of coarse, so we couldn't capture all the scales. And also the same problem has happened in other validation studies with this experiment. So we still kind of figure out why this happens exactly. Then we measured the pressures on the specimen on the specific points that they were installed also in the experiment. And we measured the velocities on the specific points that were in the flume. I would say that both of them seem quite a good comparison. So we believe that the validation study holds true for our study to continue forward into much larger problems. Okay, so moving forward to the main part of the presentation. In order to study the effects of the fluid structure interaction between solitary waves and light frame timber coastal houses, a prototype single-story house with a rectangular plan, the simplest we can find, was developed with respect to the guidelines of FEMA P499. So for anybody who doesn't know what FEMA P499 is basically a handbook of construction of light frame timber houses in coastal regions. It's not really a requirement to use the exact, let's say, methods they use, but it's a proposal and you can go beneath that. You can go. One thing that I noticed when reviewing this guideline is that it was actually the absence of an engineer in the construction of each house, because of course FEMA has been created by engineers and they had a say in it, but there's no requirement for an engineer to oversee your construction, right? So to describe a little bit about the coastal house we developed, the elevation plan is 30 feet by 30 feet. It's a single-story house. The tallest point of the house is 18 feet above ground, and it's elevated by 4 feet on 5 rows of wooden piles. So the walls of the house are framed by 2x4 studs, fairly, go to Home Depot, you can find them. They're fairly everywhere. They span 8 feet high and they're spaced 6 in center to center, which actually the spacing that FEMA proposes. The roof of the house has been braced by internal pink trusses. There are specific trusses meant for basically wooden light frame buildings, pretty standard actually. And the overhang of the roof is 30 inches. Lastly, the prototype is elevated on a foundation made of wooden pilings. Total of 29 piles were modeled. I would say that's an overkill, but we might do some testing afterwards, with each pile having a diameter of 10 inches, and each row has a spacing of approximately 7 feet. Now, since we have the house, we have to describe a wave. The bathymetry of the finite element flume corresponds to that of the flume present at the hydraulics laboratory at the University of Houston, where we will be conducting also some experiments. It should be noted that the flume's slope stiffness is kind of high, it's 1/8, which is typical for indicative of rock coast and single steep beaches. Thus, all solitary waves are expected to break, and we can see that afterwards before reaching the structure, which is situated 13 feet inland. Okay, moving forward. I want to talk a little bit more about how these houses are constructed. And this is actually the Fund element model. I think it might be interesting for me to spend some minutes here. So because the two-way FSI modeling is fairly computationally expensive, our aim was to reduce the expenses, computational expenses on the solid part. So we modeled the facade as cell elements and the studs, the king spots, and everything else as beam elements. The only thing that was modeled as solid elements was the pile foundation. Now, of course, all of them have anisotropic material properties, and they're kind of indicative of of what is being used in construction today. Okay, so as I mentioned, our first scope was to study the effect of connection flexibility. We want to actually see how the house performs under wave loading when the timber-timber connection is more rigid, in contrast to the conventional way of constructing. As you can see here, these, let's say, are proposed, as in tested, but it's a proposed moment resisting joint, which we can mount steel angles to generate moment resistance. And the other one is the strong ties for connection. A guy comes with a nail gun and just puts the studs together, which is kind of problematic. Why? Because, of course, as you can imagine, there's negligible moment resistance in this joint. I mean, you just throw it in breaks. And what happens is that they create tension perpendicular to grain. For those who know about wood as a material, wood is relatively a strong material when it comes to its strength to density ratio, but it's not a good material when you have tension perpendicular to the grain because it splits. So I'm going to tell you how we modeled in Abacus. So the first one, as moment resisting joints, we actually, we assumed monolithic behavior, like full diaphragm behavior. And the second one, it was just pin connections. No moment resisting capacity was introduced. The reason we did that is because we feel uncertain of adding it's called withdrawal stiffness into the strong tie screw connections, because not many studies have been done to this type of houses. Okay, then the second scope, as we talked about, is the effect of soil flexibility. Okay, so we have fluid structure interaction, FSI. How can we introduce SSI, soil structure interaction? One way would be to model, the soil as a 3D element. That wasn't possible because the computational expense would skyrocket. So what we settled on is using some forms of PY curves into the piles that were actually embedded in the ground. So far, we've done one PY spring from an in clay. The other one, the final science, is still running. I promise I'll get back to that. Okay, so basically, to understand the PY springs and how they behave, is that those curves were generated for static and cyclic loading. However, when we talk about cyclic loading, we mean at a quasi-static level. There was no dynamic effects inserted. So how can we implement PY springs into a heavily dynamic analysis, wave loading, when they come from quasi-static, experimental data? So what we did was that we divided our piles every 6 inches, then installed a PY spring there, and we left the pile tip here. That's what I'm referring to. We left it to rotate freely in plane, because if you see many pictures of how the foundations fail in coastal houses, you always see something that has been actually pushed by the wave and it is standing like the Tower of Pisa. So we thought that this would actually present reality. So the PY curves were assigned a nonlinear elastic in the pre-plastic portion here, 0 to C. And then there was isotropic plasticity, which was actually, it's not really correct because the soil is not isotropic plastic material, but that was the only option left for us. At this point, we might need to update here, which allows for hardening and softening. So bottom point, what I'm trying to say, we were able to capture the whole curve using this modeling technique. So that leaves us, we believe that we have captured the realistic effect of the soil structure interaction at a good margin. Okay, So we ran some cases. The first case would be the pile foundations without, just no embedment. Assume, as most structural engineers do, assume that the piles are fixed on the ground. And one with soil structure, and actually several with soil structure interaction, where the found element pile members extend into the soil. There were two embedment cases, 5 times the diameter of the pile and 10 times the diameter of the pile. Okay, so let's talk about the wave generation. We studied the house under 3 different waves. The wave height to still water level can be seen here, 0.55, 0.45, and 0.35. And you can see actually how differently they behave with the structure. As you can expect, of course, the waves with a higher wave to height ratio surge way higher than the other ones. However, even for the lowest wave to height ratio, where the wave just barely touches the structure, there is still some significant surging happening in the facade. Then we actually kind of wanted to understand how the wave, behaves with the facade. So we thought it would be beneficial for us to break down the wave interaction in different components. The first one is when the wave just makes the first contact with the house. Then we have the full surge, where basically the top of the wave here, the velocity is 0. So the wave just has stopped surging. It's going to splash back, and it's splashing back, as we mentioned. Okay, so here you can see a comparative graph on the different waves, different wave heights to still water levels for different, basically for the same model, which was with moment resistant connections. So it can be, it's kind of obvious that, of course, the waves that surge higher have a higher contact force with the house. And what's more interesting for me is that there's a sharp drop afterwards. Like after the surge, the contact forces kind of become not 0, but they are generally way less than the peak transient force. And then they are followed by smaller forces until all the water has escaped to the foundation. Okay, so let's go back to what I was promised. The comparison between the pinned connections, I would say conventional screw tie connections, and the moment resistant connections. So we ran this is the case for the middle wave height. So it's not the highest, it's not the lowest, it's kind of the middle child of the situation here. So we compared the transient peak forces, how they rise in magnitude at the connections. And as you can see, the flexible connections, which is the red graph here, experience more forces than the other models. This can be attributed to, as you can see, kind of in the movie. So what happens is when the wave crashes, it deforms the house such a way that basically more water is allowed to accumulate in the front of the facade and push the house further. That's why you have increased forces. One thing that should be noted here is that all of our analysis in regards to the solid part were limited to the linear elastic spectrum, mainly because there's no inherent plastic model for timber as of now in the framework we used. We aim to implement that, however. Here, I think this slide actually makes my point more clear. As you can see, the first, this is the house profile, like you cut it in the middle. As you can see in the first profile, where the moment resistant connections take place, we don't have much. The deformations are actually more uniform, you might say, and they're not concentrated in the place where the water hits. So again, this is the time step for the peak transient force, okay, like the biggest force you could take at this point. So as you can see here, the facade deforms greatly. More water is allowed to accumulate here, recirculate, and pushes the house more. Okay, so having said that about the timber connection flexibility, let's move forward to the foundation flexibility. Again, we studied only the middle wave with the height ratio of 0.45, and this is the analysis for only marine clay. The PY springs, as mentioned earlier, were based on Matlog's formulation. So what you can see here is that we actually have the similar phenomenon that a more flexible system receives more force. That might seem counterintuitive at first. Like, how can a more flexible system receive more force from an impact force? However, the wave loading is not a single impact. It's actually a prolonged impact. So if you can see here, again, of course, the winner goes to the screw tie connections, the conventional way of building those houses, which they receive the most force out of all the models. But then with solid structure interaction enabled, we see that the house receives kind of, I wouldn't say drastically, but maybe more forces than without the counting forces SI. As you can see down in the movie, you can actually see this for the embedment length of 5 times the diameter, by the way. The house, after receiving the wave loading, deforms in a way that stays, hanging, and more water is allowed to accumulate on the facade. And there is actually another thing that's very interesting to us is that because exactly one could oversimplify this and say that, oh, look, it looks like a cantilever beam, or maybe like a pendulum, reverse pendulum, where you have the mass on top and you just have the support on the bottom. So there is a semi-schlossing phenomenon happening here. That's why we get the consequent peaks, which are very different than all the other cases without the solid structure interaction. This mainly because to be honest, this pile embedment depth is relatively low. Like you won't find 5 diameters right now, but it still was interesting to study. Now, so what happens when you drive the piles deeper? This case would be the black graph here, where we can see again the schlossing phenomenon happening, but only in one peak. There's not like a consequent peaks. It might follow the image of the other analysis without the short foundation. So here you can see the comparison of the two movies. Of course, as you'd expect, as you drive the piles deeper, you won't get that much plastic deformations because you basically have more resistance, more solid resistance activated. And this way, the forces still remain the same, but you don't have the consecutive peaks phenomenon. Okay, so what is the summary of all this? The summary we have so far is that the flexibility of the connections and the solid structure interaction can play a role in the interaction between the ocean waves and coastal housing. I mean, that's nothing new. We were expecting that before going into the study. However, in all the cases, as long as the wave touches the structure, coastal houses will experience significant forces because they're always allowed to search on them. Here, we assumed always that the house will not be, in an angle for the wave, because when you build a house on the coast, you want to see the sea, right? So you want to build like diagonally to reduce the wave loading, and that advances in construction could be made to reduce connection flexibility or to introduce non-conventional exposed mechanisms. This goes actually to a further study we're going to do to see how we can reduce the loading by introducing something else, because our main point is that coastal houses can be actually built better to allow the water to escape to the foundation and not surge on them. And lastly, again, the study I just showed you, it's all in the elastic spectrum. So we don't really know, maybe the wave surges on top of the facade and the whole thing breaks, and we haven't seen that already. So it was only as the next step of the study is to introduce a plasticity of timber. These are the relevant applications and upcoming presentations for this study. Today was actually a crash course test, if you can imagine. Okay, and that's about it. Are there any questions?
So when you were, sorry.
Yes.
When you were modeling when you took into account the soil structure interaction, the soil interaction with the pile, did you have to introduce the third domain to your model?
No, what we actually did was basically the only thing we did was assumed that the PY springs kind of like, I mean, that's how they were formulated. They were based on the lower bound assumption, and the plasticity was only stropic. We didn't introduce anything else. If I understood your question correctly.
Yeah, it's really interesting. You did a good job.
Thank you. So are there any questions? Let me actually, yeah.
Ask online.
Yeah, I'm gonna see. I'm gonna see if there are any questions online. Yeah, I'm gonna stop sharing the screen to do that. Sorry. Okay, the chat is empty. That's a good thing or a bad thing, depending on how you interpret it. Sure. Yeah.
It's more like a question. I just wanted to clarify what you said. So for the flexible connection, you didn't have. Oh, sorry, I wasn't for the deeper file.
Yes.
That you didn't have subsequent peaks. I didn't catch why that was.
So I mean, we're still looking into it, but so far it's a hypothesis because you can't be sure of them until you have done like 1,000 analysis. So what happens is when you have like more shallow foundations, you have the wave coming through, the house is being pushed, then comes back more. Let's say because they have like, let's say 5 PY springs, the plastic deformation that these 5 PY springs can experience are limited and less than we have 15 springs. So it's more like there's, let's say, not as much controlled energy dissipation in this case. Anybody else? Okay. I mean, if there are any questions online, I think that's a good way to stop the presentation.